Welcome everyone to the Combinatorics Physics and Probability Seminar. It's a pleasure to have here today in person Bernd Sturmfels from MK Leipzig and UC Berkeley, talking about algebraic statistics with a view towards physics. We will have some time for questions. Please type your questions on the chat, and we can unmute you, and then we can hear your questions. And please, it's a pleasure to have you here, Bernd, and you can feel free to start.
Okay, so got it. Well, thank you very much. So it's great to be here. Hi to people online. So yesterday in the afternoon, we had a get-together over at Harvard on statistics. Tomorrow and the next 3 days here, we're going to talk about connections to physics. So this is the in-between. So statistics is a subject that studies graphs, and physics is a subject that studies graphs, and sometimes we look at yellow books. So let's start out with basics of statistical models in discrete settings. So for me, a discrete statistical model is any subset M of the n-dimensional probability simplex. So this is the open simplex of positive vectors P0, P1 up to Pn, whose coordinates sum to 1. Now, data, of course, are very important. So we're going to make a bunch of experiments, and each outcome is one of these numbers, 0, 1 up to n. And so by ui, I will denote the number of samples that were observed to be in state I. I'm going to summarize my data in a vector u, and I might divide by the grand total. So I have a vector u of positive rational numbers that is in the simplex. So that's my data. Now, in likelihood inference, the function I'm interested in is the maximum likelihood estimator of the model. And this is the function that takes a data vector u anywhere in the simplex and maps it into the model. So it seeks to find the best point in the model, and by best that best explains the data. And best in this setting means we're maximizing the log likelihood function. So the function we're maximizing is the following. I take the sum I from 0 to n, ui log pi. So this is defined on the open simplex. So log of a positive number is well defined. And I restrict this to m, and then I try to find the maximum. Now, of course, it could happen for special u, there's more than one maximum, but typically we're going to assume there's unique maximum. And then the function that results, I will call the MLE, the maximum likelihood estimator. Now, this function is a retraction onto the model. So if you're on the model already, so think about the model as some curve or surface. So if your data lies exactly on the model, then it gets mapped, the point gets mapped to itself. Right? So this is a retraction. This retracts the subset onto, so it's a map from the simplex to M. That's the identity on M. Now, in an algebraic setting, M will be defined by polynomials, polynomial equations, possibly inequalities, which I'll mostly disregard. So for me, if M is a variety, then this function I is an algebraic function. So I can write the critical points in terms of polynomials. And the reason is, well, the logarithm is not a polynomial, but the derivative of the logarithm, of course, is 1 over x. So everything becomes a polynomial when I write down the critical equation. So being an algebraic function means that there's a degree, and that degree I will call the maximum likelihood degree of M. So this is the algebraic degree of phi, and this is an intrinsic complexity measure for likelihood inference on the model, ML degree. So another way of saying that, so I know that Chy likes rational points. So if the ui are integers, typical integers or rational numbers, and then the true optimal solution pi hat computed numerically, say by Simon, has coordinates that are algebraic numbers over q, and then this is the degree of the field extension. Okay, so this comes with the Galois group and all that kind of thing. So here's a cartoon. So this is a book I was involved in many years ago called Algebraic Statistics for Computational Biology. So typically the dimension of the simplex is very large. So I have this very high dimensional probability simplex. In red, I have the model here, this little curve. The data called U in this talk is some point here, and I'm trying to find the best point, the closest point. But you know, this is not the closest point in Euclidean sense, but it's in the likelihood sense that I indicated. Now, often in statistics, these models, they come in a parametric form. So there's some parameter space, some low dimensional parameter space that parameterizes the model by some map F that's ideally one-to-one or locally one-to-one identifiable. And then we can either ask for the optimal distribution or the optimal parameter vector over here. So that's the cut term. Now, the simplest model that we start with is independence for two binary random variables. So we have two binary random variables. So I ask each of you, you know, do you wear glasses or do you wear a mask? Right. So the question is this independent? So, you know, then P0 is the probability of mask plus glasses, mask no glasses, glasses no mask, neither, right? And so independent would mean that that the rank is 1. Okay, so the independence model geometrically is now this surface inside the three-dimensional tetrahedron. So this is rank 1 2x2 matrices. In geometry, that's called the Cegm variety. And so that's our model. And in this case, it's very easy to solve the optimization problem. Namely, here's what you do. So the data is a matrix U. So I'm asking each of you, you have people with glasses and mask, glasses no mask, mask no glasses neither. I divide by the grand total. And then the optimal solution is this rational function. So it's given by taking the row sums of the data, the column sums of the data, you multiply them to make a rank 1 matrix, and you divide by the square of the sample size for proper scaling. So this we teach to freshman biologists in Berkeley. So in 10B, you know, we teach this formula. So what I want you to notice here is that this is a rational function. So the ML degree is 1. An algebraic function of degree 1 is a rational function. I further want you to notice that the coordinates of this rational function factor into a product of linear factors with positive coefficients. Let's do another example, it's one of these probability trees that you see in high school. So let's do the following experiment. You have a biased coin and you flip it, right? And you don't know the bias. And if it shows heads, if it shows tails, you're done, right? If it shows heads, you flip it one more time, and then you're done, right? So there are 3 possible outcomes. So one outcome is just tails, or heads, tails, or heads, heads, right? So there are 3 possible outcomes of this experiment. The probabilities I'm going to call P0, P1, and P2. So this model is parameterized by the one-dimensional probability simplex. So the bias is S0, S1. So S0 is the probability of heads. S1 is the probability of tails. Of course, you know, they sum to 1 in the application, and that's unknown. So this is a parametric representation of a curve inside the triangle, delta 2. Now, the implicit equation is this, I can write this as this homogeneous quadratic equation. So this is a parametrized quadratic curve inside the triangle. Now let's compute, we do this experiment 1,000 times, right? So I give you this coin, right? And I let you throw this 1,000 times. And then U0 is the number of times you saw heads, 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 tails, and just tails. And now I want you to find the best point on the curve. Well, again, this is an ML degree 1 model. So the way you find the optimal parameters is as follows. So in the numerator here, in the denominator, this is the total number of Toyn causes. Right? So as you do this experiment 1,000 times, this expression is the total number of times the Toyn were caused. Now, this is the total number of times you saw heads. This is the total number of times you saw tails. So these are just the empirical fractions of seeing heads and tails, and this does indeed optimize the likelihood function, but we want to plug this now in and find the best point on our curve. And so by plugging this in here, you get these expressions. And again, this is a rational function of the data. It's a rational function on projective space, right? Numerator and denominator are homogeneous of the same degree. And it factors into positive linear factors. Okay. Just interrupt me if there's any questions. Okay, so I sort of dwelled a little bit in these examples on ML degree 1. So let's answer the question how to be rational. Right? How can you have a rational MLE? Well, let's do an analogy. Let's pretend for a moment we did this in Euclidean space. So let's suppose I have a model M that's in Euclidean space. And let's take our retraction to be the nearest point map. Right? So I have some model. I have some model here in Euclidean space, some curve. And then I want to I look at the map that maps it to the nearest point. So I claim that this function is a rational function if and only if M is a linear space. Right? Now, certainly if it's a linear space, then that's a rational function. You learn in high school how to write down, the closest point on a line in 3 space, but that's actually a converse. So if you have something that's nonlinear, like a sphere, then you have to write down a square root. So whenever you have something nonlinear, you have to have a square root. So the question is, in the context of statistics, what plays the role of linear spaces? So who are the models that play the role of linear spaces? Which M have the ML degree 1, such as this Segre surface? And an answer was given by Juniher. So he wrote a paper called Varieties with Maximum Likelihood Degree 1. This was based on earlier work by Kapranov, so-called the Horn uniformization. This was in the complex algebraic setting. So we refined this to real algebraic geometry in this recent paper with Eliana Duarte and Orlando Marigliano. So there is now a very, very nice understanding of discrete statistical models with rational MLE, although there's a lot of open problems. So there's an answer. And part of this answer is they all look like this. So it turns out whenever this function is rational, it factors in each coordinate as a product, alternating product of linear forms with positive coefficients. So this week, we like positive things, we like positive geometries, and we like positive coefficients. Okay.
How about the model itself?
The model itself is so there is a structure theory. So I didn't state the result. So the structure theory, so that it basically is derived from dual varieties to toric varieties. So you start with a toric variety, you look at the discriminant, the projectively dual variety, you look at any polynomial that vanishes on such a dual variety, and from that you can derive it. Okay? So it has to do with polynomials in the ideal of the dual variety. Now the dual variety, usually a hypersurface, but often not, actually, sometimes not. So it's actually quite an interesting story. So there's a lot behind this, right? But the only take-home message here is that even in this case, so I want to remember products of linear forms with positive coefficients. So let's cast the question in the context of projective geometry. So let's say M is any projective variety. Let's say a real projective variety with some reasonable hypotheses, the real smooth points being dense, for example. I want to think about P0, P1 up to Pn, my homogeneous coordinates on projective space. I think of these as the probabilities. Then I have this data vector U, positive integers typically. Then the likelihood function. So this is the function whose logarithm I had 13 minutes ago. So the likelihood function is this rational function on projective space. So in the numerator, I have P0 to the U0, P1 to the U1, Pn to the Un. But then to make it a rational function on projective space, I have to divide by the grand total raised to the sample size, right? So now both numerator and the denominator are homogeneous of the same degree, which is the sample size. So in the application to statistics, this expression is 1, right? But to do this in projective geometry, I'm going to look at this function. So this is a rational function on my model to complex numbers. Now notice that in this formula, you see an arrangement of n plus 2 hyperplanes in projective n space. Right? So there are the n plus 1 coordinate hyperplanes in the projective space, and there is one more hyperplane, n plus 2 hyperplanes in projective n space. That's our frame. Okay. So here's a theorem that sort of summarizes the story. So the number of complex critical points of the likelihood function, or the logarithm thereof, is independent of u, provided u is generic. Okay. So Michna yesterday attributed this to Deligne, and that's in fact correct, right? This has to do with logarithmic sheaves. So this is the ML degree. So the maximum likelihood degree of the model is exactly this number of critical points. Okay? This is the number of critical points. Now, under some hypotheses, so if m minus h is smooth, so what's that? So m is my variety, and I remove the intersection with n plus 2 hyperplanes. So I have this distinguished hyperplane arrangement. I remove from the model whatever lies in the model. And if this complement, so this complement is a very affine variety. So it turns out this is so very affine means a subvariety of a torus. And if this open, very affine variety is smooth, then the Euler characteristic agrees with this number. Then it's just a topological Euler characteristic. Now it could happen in many applications this model is not smooth. Then you have some other characteristic classes. So then the ML degree is the so-called CSM class, the Chern-Schwarz-McPherson class, and there's a little bit of fine print that I'll spare you. But basically, the take-home message, it's the Euler characteristic of the open variety. Now again, in algebraic geometry, I would say, well, that's pretty nice, right? Let's do a resolution of singularities of this pair and replace this, but you can't. And so in practice, you can never actually carry out the resolution, and you don't want to. Okay, so but it can happen that the open variety is smooth. In this case, it's the Euler characteristic. So here are some references. So this Euler characteristic observation was made a long time ago in a paper with Catanese, where we introduced the maximum likelihood degree. Again, June worked on this as a survey. This is in sort of an expository paper that we wrote together called Likelihood Geometry, and it's an active area of research. So here's just one recent reference by Botong Wan and Jose Rodriguez called Computing Euler Obstruction Functions Using Maximum Likelihood Degrees. And this is just to say that the application to topology and singularity theory works both ways, right? So you can use topology and singularity theory to count the number of solutions to our equations, but you can go also the other way around. So they used it the opposite. They said, let's count the number of solutions to our equations to say something about something that people in singularity theory and topology are interested in. Okay, so that's the setting of projective varieties. Now, what if the projective variety is a linear space? So we're going to learn tomorrow morning from Federico and Chris that, there's a very nice interplay between linear varieties and nonlinear varieties. So let's suppose my model is actually a linear space. So let's say my projective variety is a linear space. Well, in this case, there's some very nice combinatorics. So in this case, so this is sometimes attributed to Marchenko. So in this case, the ML degree is the number of bounded regions in the affine hyperplane arrangement. So this is an arrangement of n plus 2 hyperplanes, the aforementioned n plus 2 hyperplanes intersected with M. Right? So M is some linear subspace of some dimension. But now I look at the n plus 2 hyperplanes inside that subspace. And I'm going to call this distinguished hyperplane the hyperplane at infinity. So now I have an arrangement of n plus 1 affine hyperplanes in an affine linear, in a linear space of some dimension. I count the number of bounded regions, and that is the ML degree. That's the Euler characteristic. Now, furthermore, for positive data U, so in the application, these are typically positive integers. Every complex solution to our equation is real, and there's precisely one solution every bounded region. And Well, a couple orange keywords. So there's combinatorics and linear algebra, matroids, Zaslavsky, and so on. So this is something that all of Lawrence students know very, very well, especially after this semester's lecture taught by Chris. So here's pictures of hyperplane arrangements. So if you see a picture like this, the analogy would be two bounded regions. Here it would be 6. 1, 2, 3, 4, 6. Okay, so this is for linear models. Well, this is a very special case of this. So here again is the linear theorem. Now, how do you pass from linear to nonlinear? Well, this is sort of important because our group, a group that Simon and I are in Leipzig, is not called the linear algebra group. We're called the nonlinear algebra. So we like nonlinear algebra. So here's a textbook, Invitation to Nonlinear Algebra. If the model is nonlinear, well, then you have to actually compute these critical points of the likelihood function. And in practice, we're using reliable numerical methods. So maybe as a sort of way of aside, so for many, many years, for 30 years, computing in algebraic geometry meant symbolic computing using Rupner bases, Macaulay, Sage, Magma. You guys probably like Magma. So for many, many years, it meant symbolic computing and the workhorse being Rupner bases. But now there's sort of this new paradigm of numerical methods, numerical nonlinear algebra. In particular, a piece of software that we like is called homotopy-continuation.jl. So this is a Julia package for solving polynomial equations. And that can go just much further. So it can do much bigger problems. So we had this notice this article called 3264 conics in a second. So in the meantime, it's actually a fraction of a second. So there's this website. So you can tell, your nephew in Romania, middle school students, they can go to this website. They can make their own 5 blue conics, click a button, and then less than a second later, the 3,264 solutions come back. So there's a website that you can play with. But what's important here that these methods, they're fast and they're actually reliable. So in the sense that there's a button that you can press that says certify, and then it does some additional computation. And if you're lucky, it comes back with a proof, okay, that your solutions are correct. So these methods are sort of almost as reliable in many cases as symbolic methods.
So correct and complete or correct?
Correct and complete, and maybe we'll leave the details for discussion. So Simon is the expert on this. So if it comes back, it says, I certified what you have, then that means every solution that you found is a true solution. They're all distinct. Now, complete is a bit more tricky, right? So to complete, it would be nice to, so let's say they come back and it says the answer, the number of solutions is 3,262. Okay. Well, then you don't know, right? This might be the true number, might not be the true number. But if for other reasons you knew that this is the correct number, and if that matches, then you're also complete, right? So if you have some insight, if you're able to do some other math that predicts the number ahead of time, then you get correctness and completeness. But completeness usually involves another step that you want to know this number ahead of time. Usually. Not always, but usually. Okay, so this is the end of the statistics part. So maybe this would be a good moment to pause. So 15 slides to go, 14 slides to go. Are there any questions? So this is the problem we want to solve, right? We want to maximize the log likelihood function or the multiplicative version, the likelihood function. We're taking the derivatives on the model, we're setting them to 0, and this is a system of polynomial equations that we solve. If the given model is linear, then we're precisely, in the setting that will be discussed tomorrow morning of matroid theory and the algebraic geometry of matroids. In general, we are in a more general world of topological invariance of pairs. So we have a projective variety with the divisor removed, and I think there's a lot of room to apply advanced techniques. I don't know, Hodge ideals maybe in the future could be relevant, but there are lots and lots of problems. Okay, so then let me slowly come to the connection to physics. So tomorrow we'll have this workshop called Combinatorics and Nonlinear Algebra inspired by physics. So let's move a little bit, towards those inspirations. So when I look for a model for 6 particles on a line, the line is the complex projective line, okay, also known as the Riemann sphere. Okay, so the moduli space M06 is the moduli space of 6 labeled distinct points on the line, on the Riemann sphere. Now, the way we like to write this, so if you're a student of Lorem, the way we like to write this as a Grassmannian. So we take the Grassmannian of 2-dimensional vector subspaces of a 6-dimensional space. I take the open Grassmannian, so I only take the part of the Grassmannian where all 15 Plücker coordinates are non-zero. So this is the open Grassmannian. Now, each point here can be represented, as I said, either by the 15 Plücker coordinates or just as the row space of a 2×6 matrix. But then there's a natural action of the 6-dimensional torus, really effectively 5-dimensional action that I mod out. Right? So it turns out that this space of 6 points on the line really should be thought of this way. I take the open Grassmannian, mod the torus. Now, first of all, this is a 3-dimensional variety, right? So if you have 6 points on the line, right? So the first 3 points, you can call them 0, 1, infinity. And then there are 3 more points that can travel around freely. So this is a variety of dimension 3. So I claim this is a very affine variety. That is to say, I have to write this as an open subvariety of a torus. And here's how you do this. And I'm going to embed this. I'm going to show this in the setting that we had 10 minutes ago. So I'm going to realize this as a linear space, a 3-dimensional linear space in P8. N is 9. Okay. Then I have the 10 distinguished hyperplanes that I rip out. And this is the realization. So let's take this 2×6 matrix. So I pick the first, second, and third point fixed. So I pick this sort of funny identity matrix here. This is just for combinatorial reasons. I like this funny identity matrix. This is 0, infinity, and then the 1 point. And then the 3 middle points I scale. So there's x1, x2, x3 are free parameters. So these x's are distinct complex numbers, okay? And different from 0 and 1. Not 0, not 1, and distinct from each other. And then this is a representation of this open, it's a 3-dimensional open variety, very affine. Now this embedding into P8, well, what I do is I look at the 15 2×2 minors. Of those 15 2×2 minors, 6 are constant. They are 1, for example, right? So this minor is 1. So I take the 9 non-constant Plücker coordinates. These are they actually depend on x1, x2, x3, and they're linear, right? So every 2×2 minor that involves all these x's is a linear expression, and here they are. So for example, let's say P5, 6, right? This is 1 minus x. So now to make the connection to statistics more transparent, so I do a little bit of cosmetics. I divide by 3s and 9s. So I scale them, by dividing by 3 and by 9. And the reason is I want them to sum to 1. I want to be exactly in the statistical situation. So this is a linear model on 9 states. So the outcomes are, I can perform an experiment, and the outcomes are 2, 3, 2, 4, up to 5, 6. And this model has 3 parameters, x1, x2, and x3. And it's a linear model, right? So I have a linear space in P8, and then a 3-dimensional linear space in P8. I rip out the 10 distinguished hyperplanes, and this is what I get. Now, this is the log likelihood function, right? So the u's are the data, and the logarithm, the sum of the uij times the logarithm of pij. Now, this in physics, in particle physics, is called the Chy model, due to Freddy Casasso and his co-authors. And so their paper was called Scattering Equations and Kawai-Llewellyn-Tai Orthogonality. Okay, so this is exactly the model for n particles on the line. In a couple moments, I'm going to talk about generalization, the Cegm model. called, paper is called Scattering Equations from Projective Spaces to Tropical Rosmanian, and E is Nick Early, who sits right here in the first row. Answer all questions. Now, in the physics context, it's not called the log likelihood function, it's called the scattering potential. So this is the scattering potential for this model. The derivatives, in statistics, they're called the score equations or the likelihood equations. So those are the ones we set to 0 to compute critical points. They're called scattering equations in physics. And what we called Mij, which were our data. So our data, so Uij, right? So how many people have no glasses and wear a mask? Those Uij, they are called the Mandelstam invariants. And the goal is the same, to maybe optimize this function, compute critical points, all critical points, and so on. Okay? So that's our first physics example. So let's do an example. So we picked some Uij, and you calculate the 6 critical points, and then you verify, Barchenko's theorem. So there's 6 complex solutions. All 6 complex solutions are real. Okay. Notice if you look at the ordering of these coordinates, you see all the 6 permutations, right? Smallest, higher, highest, and then the 6 permutations, right? So there's 6 solutions, and the increasing one, right? The first one, the increasing one, is the one that actually gives the MLE in the statistical sense. So the increasing one makes these expressions positive. So this is worse statistics. We want these things to be positive. So that's the actual MLE. So let's note that Barchenko was right? So all 6 solutions are real. For each permutation, we have one solution, so that's between 0 and 1, it's in the cube, and there are 6 bounded regions. So here, if I take this arrangement of 9 affine hyperplanes, affine planes in 3-dimensional space, and this arrangement of these affine planes makes 6 bounded regions, one for each permutation. Okay? So it's a compact version of the AN reflection arrangement. Okay? So, okay. So let's do this for M points, so same thing. So now I take M points on the line. So I have this open moduli space M0M. So same construction, I take the Grassmannian G2M, all the non-zero political coordinates, mod the torus action. Again, I write this now as a 2x M matrix. So I start with this funny identity matrix. I end with this 1, 1 point, and everybody else in the middle has an M-3 free parameter. So this is a linear model. Again, the 2x2 minors are linear expressions. Right? So this is a linear model. It lives in Pn, and the number of states is the number of non-constant political coordinates. Right? So the M choose 2 political coordinates, but I only take those that actually involve an X, and those are M times M-3 over 2. Okay? Now, then the measurements, what I think of as the measurements are the Mandelstam invariants in physics, and they're not quite measurements. They sort of have a different role, and the gentleman in the first row will tell you what they mean. So the CHY scattering equations, so they characterize the critical points of the log likelihood function of the scattering potential. The ML degree is M-3 factorial, right? So M equals 6, we have the 3 factorial. And then for positive U, all the critical points are real. Okay. Now I worked on this. We got into this last year and a half ago with Simon. So Simon, who is here, we wrote a paper called Likelihood Equations and Scattering Amplitudes. And we were sort of happy to discover this connection between the scattering equations and maximum likelihood. And we started computing using the aforementioned Julia package, homotopy continuation.jl. And we were amazed how well this works. So we did some calculations. So for example, the number of particles on the line is 10, 11, 12, 13. So that's a statistical model with this many states, right? Remember, this number is M times M-3 over 2. And this is already like 44, 65 states, okay? Now the number of solutions, the ML degree, the number of bounded regions is M-3 factorial, and the factorial grows, right? So here's the M-3 factorial. And the time it takes to compute a first complex solution. So the way this works is you sort of use general complex, you make a first complex solution. So even for this one, you find the 5,040 solutions in under a second, just like the 3264 conics. But this is quite impressive. So if you have 3 million solutions, and this is found under an hour, right? Now then, once you have a first complex complete solution, then to find the real points for real data is in this range, again measured in seconds. And then the last time is the certify. So certify is you press the button, right? So this is correctness. Are these actually this many distinct solutions? Now we know from combinatorics, we already knew this upper bound, right? So we know the upper bound for other reasons, so we get correctness and completeness. Okay. So we were amazed, right? Because this particular system of equations, this sort of beat our expectation. This even worked better than we thought, but this is off-the-shelf software, and this really worked very well. So here you have 3 million solutions, and you find them, in the order of minutes. Okay. Yes.
I imagine you're doing like ball arithmetic.
I'm sorry.
I imagine you're doing ball arithmetic.
For this, so yes. So for the certification, so there's interval arithmetic that's used. So this is the reference by Breiting, Rose, and Timmer. So there are two stages. So the first thing is you find numerical solution, approximations of the solution using any method whatsoever. Right? So you find 5,000 points using whatever method, whatever stupid method. You find 5,000 numerical points that you believe are close to the real solution. Now, what does numerical mean? Numerical means rational coordinates, right? So if the coordinate is 7.94328, in your head, there's a real number, but this is actually a rational number, right? So you find these 5,000 rational approximations called floating point numbers to what you believe are the true solutions. Okay? So then there's a certification step, and then you do interval arithmetic that certifies that you believe actually corresponds to a true solution. So this is actually, so I distinguished earlier, like half an hour ago, I talked about the distinction between numerical computing and symbolic computing, but actually numerical computing is surprisingly symbolic. Okay, so Cegm, right? So this is the project Nick was part of, so it's the same thing, but in higher dimensions. So now it gets a bit more interesting. So we take a modularized space for m points in general position and projective k-1 space. So this is again open. So I do not yet compactify. This is the open space. And but the definition is the same. So I take the Grassmannian, I take the open part, mod the torus. Right? So this is the space of m points in projective k-1 space, no k on a hyperplane. No k on a hyperplane. Now again, this is smooth. It's a very affine variety. It has this dimension, k-1 times m minus k-1. So those are the regions. When you draw Playback graphs, you see this many regions. Okay, so that's the dimension of this very affine variety. Now, we have again this model, the Cegm model. So the Cegm model now is a non-linear statistical model. And but it's smooth. So the ML degree is the Euler characteristic. So this space has an Euler characteristic, and that is the ML degree. Now these numbers become a bit more interesting. They're more interesting than the factorials we had. So let's do this in the plane. So let's take the space of m points in P2, no 3 collinear. Well, so it turns out that, so here again is the statistical model, is the number of non-constant Brückner coordinates, so 6 points, 7 points, 8.9 points, and so on. And these are the known values of the ML degree. So the number 26, I first learned from a paper of Nick. That sort of got me into it. I saw he had the system that, I made 26 solutions. I said, hey, what does this mean in statistics? And they knew this number, and then, it gets more complicated. So this was known. Now, these ML degrees were known thanks to the physics literature, and There was also work by Thomas Lamb that was very interesting. So he used matroids and finite field methods. So he used the beta, so you can use the Bayes conjectures to relate the topological invariance. So like Euler characteristic, you can, under some hypotheses, you can compute, topological invariance of the complex smooth open variety by counting points over finite fields. And in these situations, he was able to use existing results from coding theory, and he sort of got up to this point, and then this was also predicted at the last point. So when we started out with CMOD, we were able to compute the first 3, but we were not able in the first project to compute the 74 million. Okay, but we confirmed them. There are lots of open questions. So can all the critical points be real? What about larger K and M? Now, those who think about matroids and realization of matroids, so there's not going to be any general formula for K and M, right? Realization space of matroids, the wild, universal problem. So we cannot expect a general formula, but we can, try to go as far as we can. Okay, I'm going to come back to this number at the moment. But so these first 3 numbers, again, with the same methodology, were computed in the original project with CMOD, were confirmed. Amplitudes. So let me jump right in. So this is another formula that I saw in a paper by Nick, and this is this is for the Chy model for this model. So I take the model for 6 particles on the line. I take this 3-dimensional linear model. I'm going to write down the scattering amplitude. I'll tell you in a moment what a scattering. I first show you this, and then I'll say what the scattering amplitude might be. Okay. Well, it's a rational function in the data. Remember the data here were the Mandelstam invariants. They were called Uij. Okay. Now you see things that have 3 indices. So if you have U, 3, 4, 5, this is simply the sum. Right? So by Uijk, I mean Uij plus Uik plus Ujk. Just a convention. So now everything is this is a rational function in the Uij's. Okay. Now this rational function has 14 sum ends, right? So it's written as a sum of 14 reciprocal products of 1 over a product of 3 linear forms with positive coefficients. Of course, 14 is the Catalan number, right? So the number of triangulations of the hexagon, the vertices of the isosahedron, and so this is the kind of rational functions that are of interest, right? Now, of course, you can understand this combinatorially. Once you have this combinatorial formula, that's great. You're home, right? Then you can evaluate this, and you have a complete understanding. You can still ask many questions, but that's sort of the combinatorial threat, right? But let's pretend for a moment we do not have this formula. You can also compute these things numerically by summing residues over all critical points of the likelihood function. So you can all compute numerically, reliably, verified with interval arithmetic, all 5,000 critical points, and then by doing a certain sum over the critical points, you can also, oops, what happened here? I lost it. Okay, let me try it one more time. How did this? Anybody have a suggestion?
Slide the center bar over.
Slide the center bar over. Oh, I mean this thing. Ah. Well, no. I can try to close the email, but first let everybody read my email. Okay. Okay, how do I close? How is this? Okay, so so we looked at these papers by Nima, co-authors, including Thomas Lamb, called Positive Geometries and Canonical Forms and Stringy Canonical Forms. And we said, well, what does this mean for statistics? So we defined positive statistical models and their amplitudes. And we observed that this includes all toric models, all linear models, and all ML degree 1 models. And There was a follow-up work that was presented yesterday in the statistics seminar by Simon called Bayesian Integrals on toric variety. So let me give you what I think of as the definition of these amplitudes. But before I do that, let's look at the likelihood function again. Right? So the likelihood function for a parametric statistical model, it looks like this. So P0, it depends on some parameters x, maybe x1, x2, x3, right? Remember the cartoon from the old biology book, where I have this like wiggle in the triangle, and it's parameterized by some low-dimensional parameter space. And this is the function I'm interested in, P0 to the U0, P1 to the U1, Pn to the Un. So this is a parameterized model, and I like to think about this as a projective model. Right? Now, the title of this slide is Frequentist to Bayesian. Now, in statistics, historically, there are two flavors. There are frequentist statisticians and Bayesian statisticians, and they used to fight. Okay? Now, what about math? What's the analog in math? Well, our purpose in life is to teach calculus to the unwilling. And there are two flavors of calculus, right? There is differential calculus, and there's integral calculus. Right? Now, what do we teach then? Well, we teach differential calculus, so differential calculus to optimize functions, right? To find the highest point, right? So we want to maximize a function, the derivative is 0, and that's why we teach differential calculus, right? On the other hand, there's the integral calculus, and that we teach to measure the area under the curve, right? And these statistical concepts are the same, right? So frequentist statistic, that's basically the statistics of differential calculus. And Bayesian statistics is the statistics of integral calculus, right? So we have this nice likelihood function. And until now, we optimized it. We did differential calculus. We wrote the scattering equations. But now let's integrate it. Right? So let's do some differential calculus. So this is called a marginal likelihood integral. There is a measure on the parameter space against which you integrate. That's called the prior belief. So the measure is the prior belief. And the amplitude is a limit of a certain transformation of this integral. So you do something to these exponents and you sort of send them to 0 in a controlled way. And the limit object will be a rational function of the use. And this rational function is called the scattering amplitude. So here's a theorem. So the amplitude of a positive model defined here is a rational function of the data. It's the volume of a certain polytope, a dual polytope that depends on you. So you can write down the Newton polytope, you pass to a certain dual, but more importantly, you can compute it from the toric Hessian of the log likelihood. So I'm summing over all critical points, over all 6 or 70 million critical points here. And then here's what I do. I take the Hessian of the log likelihood function, is a slightly modified Hessian. I take the determinant reciprocal and I add this up, right? So these are, of course, algebraic functions, but then it's invariant under the Galois group, and you happily get rational functions like this, okay? Now, again, I like this very, very, very much because this is related to a topic that was studied before in algebraic statistics. So my last talk at Harvard over there, which I think was the very first post-Lauren combinatorics seminar at Harvard, okay, and I think you were there. I spoke about this paper. Okay, that was the title talk, moment varieties on measures of polytopes. And in the meantime, it's been realized, thanks to Christian and many other people, that this is related to Wex-Press coordinates, and this is really the positive geometry of a polytope, right? So think about the positive geometry of a polytope. It's related to the positive geometry of the toric variety by the moment map. And so this is a sort of a nice story. Let's see in the case of wearing glasses or not and wearing masks or not, right? So this is the independence model, the Segre surface that we saw at the beginning. So in this case, the relevant polytope is the unit square, 0,1 squared, times the sample size, scale it by the sample size. Now then we're going to shift this to make the origin and the interior, so to shift this by this vector, U2 plus U3. Then you dualize the polytope. This is another quadrilateral, and you measure the area. And the area is going to be this expression. Now this expression is a rational function whose ingredients in this case are the same positive linear forms that we saw, but it's not homogeneous of degree 0. It's homogeneous of degree minus the dimension of the polygon. It's homogeneous of degree minus 2, right? So this is quadratic, that's quartic, and so the difference is the negative of the dimension of the polygon. Okay? And so this is something, we're trying to explore. We discussed, as I said, in the context of Bayesian statistics. And I think this is something that be still very interesting. So I like to use the remaining minutes. Do I have 9? So the remaining 3 hours, I'll talk about this paper called Likelihood Degeneration. So this is a 6-author paper. And there's sort of different points of entry, but let me start with tropical MLE, the tropical MLE. Right? So now we're introducing a small positive parameter t, that's sort of small and positive. Okay? So algebraically, we're working over a valued field, such as the Puiseux series field over the real numbers. This is a real closed field, has index 2 in its algebraic closure, the complex Puiseux series. So now the data, let's simply assume that the data are now in this field. They're not real numbers or integers, they're in this field. So every ith coordinate of the data point is a scalar in this field. So it's alpha I to the wi plus higher order stuff in t. So these wi are rational numbers. Now then I can solve the equations, right? There's going to be ml degree many solutions. The number of solutions is still the same, right? But now the solutions, they have coordinates in the algebraic closure. So the jth coordinate of the optimal point will be beta j times t to the qj plus higher order terms. So beta j is a non-zero complex number and qj is again a rational number. So tropical problem is given the tropical data. So given the exponent w, directly predict the tropical critical points. Yeah, I wish I had 3 hours. I don't, right? So this slide is called Numerics Meets Tropics, Happiness Both Ways. So numerical math and tropical math, they're very much in harmony, right? So let's illustrate this. Let's solve the quintic. So t is a scalar here. So I want to write x as a function of t. So these are the 5 classical solutions written as a series expansion. And you notice, right? So the lowest order terms of t to the 0, t to the 0, t to the 0, t to the 1, t cubed. So this is the lowest order information. So the valuations of the solutions are 0, 0, 0, 1, and 3. Now this can be used both ways, right? So we can use tropical methods to help numerics. Maybe we can try to identify the tropical solutions. So we can look at this ahead of time. Number theorists call this drawing the Newton polygon. So you draw the Newton polygon, you read off this magenta stuff, but you can use this to build better homotopies for numerical solving over R or C. But you can actually go the other way. So you can use numerical methods to learn tropical information. You can use advanced numerical tools to actually solve these for smaller and smaller t. Right? So suppose I can accurately solve this for t 10 to the minus 3, 10 to the minus 5, and so on. Then from the resulting accurate numerical output over C, I can learn this stuff. And we use both directions in this project. So this is happiness both ways. Linear models. Let me state one theorem about linear models because, Chris and the students in this course like matroids. So let me tell you a theorem about matroids. So matroids, MBC bases and so on. So let's say X is a linear space and project, a linear subspace of Pn viewed as a statistical model. Now we can tropicalize both X and its orthogonal complement. So this is over the reals, right? And we can do the following. So I claim if the tropical data vector is sufficiently generic, then the following intersection consists of an L degree many distinct points. So here's what I do. I take the tropicalization of X. It's the Bergman fan. I take the tropicalization of X perp. That's essentially the Bergman fan of the dual. So these are two tropical linear spaces of complementary dimension. Okay? I shift one of them by the tropical data. Right? So now I have these two fans, but they're shifted. So now they meet infinitely many points, and those are exactly the solutions. Right? So this is the solution to the tropical MLE problem if the model is linear. Now, are there some interesting linear models? Yes, there are interesting linear models, such as M0n, right? There are interesting linear models, the CHY. Now, if the matroid is uniform, you can even write this explicitly, and then the number is just n choose d. Let's go over this in our 6 points on the line example. So that's this slide is called tropical CHY scatter, right? So this was, remember, M06 was a 3-dimensional linear space in P8 given by our arrangement of 9 planes. So let me pick the tropical data to be this, right? So these are now the tropical Mandelstam invariants. I'm going to pick them to be 12, 6, 9, 12, up to 3. So there are 6 critical points, right? So I claim that this combinatorial intersection will make 6 intersection points. So again, I take the Bergman fan, I take the Bergman of the dual, I shift it, I intersect, shift by the data. So one of the solutions is this 75200. And this is very nice combinatorics. Let me explain this. Okay, so what you do in this example, for this example, both the matroid and the dual matroid are graphic. Okay, so the matroid and the dual are graphic. So the duality is just planar graph duality. So for the original matroid, I'm drawing this green planar graph, and for some technical reasons that I don't have time to go into, there's a distinguished edge that I call 0. Okay. Now, after contracting this green edge, this is the dual graph. So the blue graph is the planar dual graph to the green left graph after contracting the orange edge. So this means, you know, every edge, every blue edge corresponds to a green edge. Right? This is planar duality. Well, here's what I do. I need to, my solutions are decompositions. I need to write the data as a q hat plus a complementary vector, such that q hat is in the green Bergman space, and the other guy is in the blue Bergman space. So that is to say, the sum ends respect the circuits and co-circuits. So let's look at this. Right. So here I'm interested in decomposing this vector as an assignment of numbers to the edges here, and another assignment of the numbers here. So for example, here this 6 is the 2, 5 coordinates, and that's the 1 plus 5. Okay, something like this. Oh no, I'm sorry. 2, 5 is this. Right, so the 2, 5 edge here is called 2, 5 here. But this respects the circuit. So the minimum is attained twice on every circuit here. The minimum is attained twice on every circuit here. So circuits here are co-circuits there are circuits here. Right? So you go in a circuit, you go 1, 9, 1, 7, and the minimum is attained twice. Right? You go here, maybe 0, 0. So anyway, yes, question.
Well, first of all, your vector, your tropical data vector, does it satisfy any relations? I mean,
No.
It's not coming.
Okay, yes. So that now I see where you're coming from. So I swept something under the rug. So here in the physics situation, there is additional hypothesis on the UIJ. So here I'm not making those assumptions. It would be very interesting to impose these assumptions and they see what they mean tropically. But for simplicity, I'm not assuming anything right now, right? So here's a game. You can try this, with your math circle club, right? So you draw a graph, you draw the dual graph, you give a bunch of numbers, and you want to decompose it into the orange vector here and the orange vector there, such that minimum is attained twice on both sides. Right? And the number is there's the right number of solutions. Now there's no time left, right? So the reason we introduced these tropical MLE is to understand what the physicists call soft limits. This is a very, very special degeneration where I have a 0, 1 vector. Topologically, this corresponds to a study of a sort of almost fibration, right? So I have m plus 1 points in general position. I can drop the last point and I can look at that map, right? Now, if this were a fibration, then I could compute the Euler characteristic. If the world is good, then I could say, well, the Euler characteristic is multiplicative in fibrations. If I know the Euler characteristic here, if I know the Euler characteristic of fibers, then I can somehow get the Euler characteristic here. Now, these things are very much not a vibration. That's the whole point of universality and wildness and matroid theory. These things are very much not a vibration. But still, we can look at their fibers. Their fibers are called discriminant hyperplane arrangements. And the special loci of these non-vibrations we computed using numerical tropical happiness. We had a theorem about the discriminantal arrangement. This was kind of fun. So what is this discriminantal arrangements? You draw M points, general points in projective k-1 space. And then for any k of them, you look at the hyperplane they span. Right? So you drop 10 points in the plane, and you look at the 10 choose 2 lines that are spanned by any pair of points. Then you ask, how many bounded regions does this have? And then this is a formula. So this turns out to be for fixed k, that's a polynomial in M. And interestingly, we're building on earlier work by Takemura and others who also got to this through algebraic statistics. Okay, so time is up. So the last slide is called From Soft Limits to Hard Facts. So we were able to verify this number. This is a very, very beautiful. This was known, it was sort of believed to be this number before. So we're able to verify this 3,9 number. But even more interesting, we were able to compute the 4,8 number for the first time. So the 4,8 number was out of reach for the finite field methods that Thomas Lamb used. So this is a truly new number. So for 8 points in 3 space in general position, the Euler character is 5,211,816. And this sort of used all the techniques I described. And we also were able to answer some questions that were in the Cajazo et al. Paper on special loci for X3M. And Nick?
I'll wait until the question period. Sorry.
Okay, the question period will be in 28 seconds. So the conclusion is that for me, the inspiration from particle physics guides me and the people I work with towards new computational paradigms, in particular for inference and algebraic statistics. So in the first paper with Simon, this was frequentist, sort of likelihood inference. In the new paper, it was more Bayesian. But along the way, even if you don't care about statistics, and even if you don't care about physics at all, you can have a lot of fun with the combinatorics and the algebraic geometry. So this is the end of it. Thanks for your attention.
Thank you very much, Bernd, for a very nice talk. Now we can ask some questions. Maybe I would start here from the in-person questions, and maybe Bernd can also repeat the questions for the audience.
So please ask short questions.
Yeah, short questions.
So about the tropical data, and that was for the purpose of counting the number of counting the M algebra, right? Is there any way to help you calculate the amplitude itself?
Okay, so the question was, so we use the tropical MLE to get the number of critical points. Can we use the tropical generation to get the amplitude itself? I believe the answer is yes. So the idea would be, so here we're saying, oops, where was it? We're saying the number of solutions is some number, like, 24, right? But from those 6 or 24 points, can we use the tropical degeneration to directly tropicalize this and get, I believe the answer is yes, we haven't done that. So I think it's a very good question. The question is, can we use the tropical degeneration to learn about this rational function? I believe the answer is yes, but we haven't worked on it.
So,
Yeah, maybe you can have,
okay.
if you have time at the end.
Go ahead.
You have any questions?
Counter models where singularity, let's say, even away from, let's say, the hyperplane.
Yes. So the most models. So let me go back to this general. So the question is, are there interesting models, that actually have singularities? And the answer is yes. So for linear models, there are no singularities, and that's a well-studied situation. So there's a vast literature on hyperplane arrangements and so on. Most models have singularities. So most models in statistics, so low-rank tensors, low-rank matrices. So typically you have some rank situation, and then the objects of rank R will be singular along the object of rank R minus 1. So that's a very typical situation, and absolutely. And then you immediately, you get into this situation. Yeah, so maybe, so again, the sort of definition and basics, I can recommend this article. So Juni and I have an article called Likelihood Geometry that describes things in a more geometric way. Again, lots of open questions. It's, so here we're using it as a number, but of course it comes from a cohomology class.
What sort of Euler characteristics it's natural to take
Okay, so I don't know the answer, but people who do. So Botang Wang and his collaborators, Nero Boudouar, for example, would be able to give you a perfect answer. So we're talking to people like Nero Boudouar and Botang Wang who know this better, but there's a lot under this hood that I don't understand. There's another question back there? No.
So on the algebraic statistics side of things, there's the Gaussian analog, so the discrete sentence. I'm curious if there's a Gaussian analog.
Okay. Yeah, so the question was, so this was for discrete models. So where we have finitely many states and the model is a subset of the simplex. So Anna's question, is there a Gaussian analog? So in the Gaussian case, the simplex gets replaced by the cone of positive definite symmetric matrices. And again, M is an appropriate subset. And for the, so this has been an open question for a long time, and partly because when we write the likelihood function here, it immediately becomes polynomials, right? So we take derivatives and immediately, things become polynomial. Oh, sorry.
My question is if there's a Gaussian analog in terms of the physics.
Oh, I see. Is there a Gaussian analog of the physics? I don't know. Okay, let me answer as follows. The question was, is there a Gaussian analog to the physics connection? So that was the, let me put it here. Is there a Gaussian version of something like these models? And the answer is, I don't know. But if I were to bet money, I think there is, and it should have to do with random matrix theory. So the random matrix theory and random tensor theory, in my mind, could lead to a Gaussian version. So Gaussian unitary ensemble. So the way, random matrix theory is used in physics could lead to a Gaussian version, but that's speculative.
Yes. So just going back to where you use the toric question to define the amplitude. So yeah, just so when in the paper with Freddie and Fredo and Sebastian, we defined it using a cyclic product of minors, a cyclically consecutive product of minors. And is the theorem that is equivalent to this, or is it in some special? Yeah, I guess. So.
Okay, so the question was, so in this Grassmannian, so in the Cegm model, you use the understanding of minors to actually give a formula for this. Is this equivalent? Well, it has to, right? Yes. But this is sort of completely general, right? Maybe I should say one word. What do I mean by toric Hessian? So by toric Hessian, so rather than taking the derivative with respect to the ith variable, you apply the Euler operator. So when you do derivatives of functions, so rather than taking the derivative like this, you take the derivative like this. Okay, that's what I mean by toric Hessian. Okay?
It wasn't totally obvious.
Yeah, yeah.
That it would be
exactly. So this is a completely general formula, but it's not rational. I'm just summing of all the critical points. It would be great to go back, to the formulas that you have and see, I mean, ultimately you want to get from this to something like this, right? There's a pretty combinatorics, and here's the numerics, right? I argued that there's tropical numerical happiness both ways, but I think there isn't quite yet, combinatorial numerical happiness both ways, but there could be.
I think there are no questions online, so we can end the talk here, a discussion, or we can maybe discuss informally later if you're here. Otherwise, we can meet for the nice workshop that is coming tomorrow or is coming. Let's thank the speaker again, excellent work.